to connect this. Oh, you got it on.
Oh, you got it.
Hopefully got it.
Okay.
Yeah. Can
I just-
you
you just said
actually share?
Okay, good, thank you.
Are you also on the Zoom? Somebody should be on the Zoom to make sure.
I can.
Yesterday there was a, Dave's talk.
If stop, yeah, okay, I think I can. But that should, the Zoom should be in the email that I sent, okay?
So should I unmute myself on the?
You.
Okay.
Okay,
And
21 people in Zoom. I can hear feedback.
oh,
No, you need to.
Yeah,
okay,
okay,
now,
now it's good.
okay. Yeah,
Okay,
and,
let me introduce you and
oh,
then.
yeah. So
Okay,
is
so
it everything then?
Is it sharing screen?
it's, yeah, this is fine. In Zoom, I see this is looking fine. Can someone give me a thumbs up if you can hear us?
We can hear you.
We can hear you.
And we can hear you.
Okay, great. So we are very happy to have Ramya today here. She's an assistant professor in Department of ECE in Wisconsin, University of Wisconsin, Madison. So Ramya graduated from Caltech a few years back, where she worked with Baba Cassidy. And then she was a postdoc with Sham Kakade in Washington, right? So at that time he was, I'm just trying to think where he is. And yeah, so we are very glad to have Ramya. She has won multiple awards, and most recently I heard that she got the NSF Career Award. So great, Ramya, please take the stage.
Thank you for the introduction, Arya. I'm really excited to be here today and talking at the TILOS seminar. So today we're talking about learning from diverse and small data. And as we go through the talk, hopefully, these terms will become clearer. Let me begin with an introduction as to why we should care about learning from diverse and small data. And then I'll talk about a couple of settings, one in which we'll look at settings where we get count data and look at some non-parametric mixture problems. And then in the second part of the talk, I'll be focusing more on preference and metric learning settings and learning from diverse data in those scenarios. So machine learning for data-driven policy making and decision making is becoming ubiquitous. I mean, everybody in this room and Zoom are very well aware of it. It's being used in lots of different critical organizations that make decisions about our lives. For example, if California comes up with a policy of providing free flu vaccines for people, they'd want to probably figure out what is the efficacy of such policy is, and therefore you would need to collect some data before and after the policy is implemented, and then in a data-driven way, try to figure out how effective the policy was. So if you think about it at a high level, just a caricature picture of machine learning system, there's data going in, the machine learning does its thing, provides inference, and domain experts use those inference to make some downstream policy decisions. If we focus a little bit on where this data is coming from, and we all have heard of this old adage of garbage in, garbage out. But the reality is a little bit more nuanced, and hopefully, in today's talk, we'll see some examples of that. In particular, I'm really interested in data that goes into the machine learning algorithm, in particular for applications where data comes from us, people, right? So of course, depending on different applications, data source might be different. But here in today's talk, I'll be focusing on data that comes from people. And I like to think about how we collect data from people as like this kind of a spectrum of varying level of control we have over how we collect data. On one end of the spectrum, there is observational data. So somebody has collected the data and we are trying to make sense of it, we make inferences from it. And on the other end of the spectrum, we might have the ability to from scratch figure out how we are going to collect data. How do we come up with surveys and then designing the whole way of collecting data. And there is a whole spectrum in between where you can think of this as like human in the loop kind of settings in between, where maybe you start out with some data and then you figure out how to kind of collect more data. So in different parts of this spectrum, there is like unique set of challenges and opportunities that arise for learning from data. Today, I'll be mostly focusing on like the one end of the spectrum in terms of observational data, but I'll be happy to also talk about like query design in particular with respect to crowdsourcing or human in the loop systems, offline after the talk. But before diving more into the details, let me again give a high level kind of motivation as to why we care about learning from diverse and small data. Particularly, if we think about observational data settings, applications ranging from social sciences, epidemiology to health sciences, usually we collect data from a large population. Right? So it kind of feels like there is a lot of data because the number of people involved in the data sets can be quite large. But however, there is a couple of key challenges that I would like to highlight. One is the diversity or the heterogeneity in the data. So different people can have differences in the way, for example, either because of demographic differences or like phenotypes, if it is a health science kind of application, there can be different ways people might react to, it might not be a single model that is like really good for all the individuals on average, right? So there is usually a diversity or heterogeneity in the data. And even though the number of people in our data set might be pretty large, the number of samples that we usually have for individual can be quite small. So that's what I mean by small data in this talk is that the small data is with respect to the amount of data we have per individual, right? So these are scenarios where it's very difficult to kind of come up with a personalized model, because usually when we have a lot of heterogeneity, one way to think about this is why don't we just fit a separate model for everybody, right? But that would require too much data from every individual. On the other end, if we do the usual recipe of machine learning, where we take everybody's data together and fit something that works on average, that's not really capturing the diversity in the data. So in this setting, the opportunity kind of to think about is how can we make reliable inferences from settings where we have diverse data, and we do want to capture the diversity, but we have too few samples to fit individual models. While I will not talk much about the query design aspect today, I just wanted to highlight some of the challenges that come here. Think about settings like crowdsourcing, where you're collecting data from machine learning, or maybe social sciences, where you're collecting data through surveys and trying to make sense of preferences that people have. And the key challenges that come in this kind of setting is that usually when we collect data from people, there can be noise in the data. This can either come from, for example, in the machine learning settings, if we are trying to collect data from non-experts, then there might be noise because of that. Or even if you're collecting data from experts, there can be inherently ambiguous settings where there could be noise because of that. And the other aspect is the cost, right? It takes a lot of both time and money to collect good quality data. So usually in these settings, what we think about is how do we obtain quality data so that we can make reliable inferences from them, but in a cost-effective manner. So in today's talk, I'll be focusing more on learning from kind of the diverse data in the small data settings. And there's going to be two parts. In the first part, I'll be focusing on learning distribution of parameters. And in particular, I'll be focusing on nonparametric mixture models for binomials and Poissons. And in the second part of the talk, I'll talk a little bit about metric and preference learning and how we can make room for learning from diverse data in those settings. So let me start with the first part of the talk. So here I'll be talking about learning distribution of binomial parameters. This was work that I did jointly with my postdoc advisor Shyam Kakade, Greg Valiant and Wei Hao Kong. So this was work that was done, around the time of 2019 when I was in Seattle. So let's consider this example. Say for a large random subset of population in California, we observe, whether a person caught the flu or not for like 5 years. Okay. So now let's take a very simple modeling. I'm making very simple modeling assumption here. Every individual I has some probability of catching the flu. That's unknown to us. So we can think of this as like a coin which has bias pi, and we don't know the bias. We get to observe only 5 tosses of this coin, right? So we only get to observe 5 observations for an individual. So if we try to estimate the bias of the coin with only 5 observations, that's going to be a really poor estimate, right? Because we have too much uncertainty to determine what the bias of this very specific coin is. So the question of interest in these settings is instead, can we learn the distribution of the probabilities over the population? So each coin has a bias, so there's a probability between 0, 1. We don't know that. We only get to observe very few tosses per coin. So we don't have a hope of really estimating individual coins probability very well. But instead, can we try to learn like this underlying distribution, or like you can think of this as like a prior of these probabilities over the population? Now, why would we want to learn this underlying distribution of probabilities? This can be useful for a lot of downstream analysis. For example, epidemiologists might be interested in testing whether this underlying distribution is unimodal or binary, right? So maybe the population has a large subset of people who might be healthy and have less chance of catching the flu, but there might be smaller but not significant fraction of the population who might be more vulnerable and might be having higher probability of catching the flu. It can also be used in trying to kind of do comparative studies. For example, how does this look like for California versus Wisconsin, right? And so epidemiologists in these 2 places might want to exchange notes and see what are best practices they could potentially exchange from each other. It can be useful in estimating certain properties of this distribution. For example, what fraction of the population has more than random chance of catching the flu. In general, you can use this learned distribution as a prior for inference and prediction in the future. So, in fact, this is a question that we didn't ask from scratch. If we go back in history, it's been studied since 1960s. The earliest work I could find was by Lord in 1965, and he was studying this in the context of psychological testing. So the setting Lord was interested in is as follows. There is a study that involves tens of thousands of people. Every person is given like a questionnaire with, let's say, 10 questions. And the modeling assumption in these psychological testing settings is that everybody is assigned, is assumed to have something called a true score. So that's the probability with which an individual answers the question correctly. And given a survey with, let's say 10 questions, the goal is to kind of learn this underlying distribution of the true scores from the actual scores that people get on these surveys. Okay.
What does true mean here?
So it's called true score. That's just in psychological testing, the assumption is that individuals have like some true score. Like this is also done in like kind of SAT testing kind of set situations as well. The idea is that the marks that we get in the exam is just like a sample of what my true ability is. And so from these exam marks, you want to kind of see, okay, what's the distribution of like these true abilities of students or something like that. Yeah, it's that word true is taken from like the literature. That's what they call it. Yeah. So if we look at what this is in terms of mathematically modeling, it's a model essentially of non-parametric mixture of binomials. So there is some underlying distribution, let's call it P star. Supported on 0, 1, this is the distribution over these probabilities. So that is the true distribution of probabilities that's underlying. And from that, we draw n independent coins. So each coin's bias is drawn independently from this underlying distribution P star. Note that P star is unknown and these biases are also unknown. So what we get to observe is T independent tosses per coin. So we get to see X for each coin I, Xi, which is a binomial TPI. Now, for example, if we toss each of the coin 5 times, and the ith coins, we see 2 heads out of 5 tosses, then Xi is just 2. So equivalently, we can write a sufficient statistic for this problem if we are interested in estimating the underlying distribution. So we are tossing each coin T times. So we can think about you can look at how many coins actually saw 0 heads out of T tosses, 1 head out of T tosses, and so on until T heads out of T tosses. So I'm going to call that fingerprints. You can think of that as histogram of counts, right? So yeah, as I mentioned, this is non-parametric mixture of binomials. And so what is the goal here? That given these binomial observations, or equivalently the fingerprint that we observe, we want to estimate the underlying distribution V star. And I'm going to measure how well we do that under Wasserstein-1 distance or Earth-Moon's distance. And so let's focus a little bit on trying to understand why is this a difficult problem in terms of learning from these few tosses per coin. So of course, if we had a lot of tosses for each coin, this would be an easy problem, right? Because if we could estimate the bias of each coin very well, I could just look at the histogram of these estimated biases, and that could give me a pretty good estimate of the underlying distribution V star. But the difficulty that we have when we have is that we only see very few tosses per coin. Therefore, if we go the naive approach of doing this empirical estimate of each coin separately and take the histogram, that's not going to be a good estimate. In particular, it's going to incur error like 1 over square root of T. So just to highlight that, if let's say all the coins were just unbiased, so all the bias of the coin is just 0.5. So if I draw 10,000 such coins and just toss each of the coin 5 times and look at the observation, and then did this naive thing of estimating each coin's bias and looking at the histogram, this is what it looks like. And so this is clearly a pretty bad estimate of a single spike. In fact, what this is estimating is more towards the fingerprint or the histogram of counts rather than really trying to get to the underlying distribution. Now, here I'm showing the same picture, but now plotting the CDF. So the dark black curve is the true CDF, the dotted red curve is the empirical CDF estimated using 10,000 coins, each coin tossed 5 times. So one thing that we can ask is okay, is this actually a small data problem in the sense that is the fact of observing 5 tosses per coin actually the real problem? What if, instead of 10,000 coins, we had more coins? Would just increasing the population size help us? The answer is no. Doesn't matter if we have 10,000 or a million or 100 million, the estimated CDF would just look like that if we just did the naive approach. And that's because, as I mentioned, the approach of just estimating individual coins bias and then looking at the histogram of that is really bottlenecked by the fact that you have only 5 tosses per coin. So that's why you see the step here. And so this is just estimating the fingerprints very well rather than the underlying distribution. So, okay, so I told you that, this has been something that people have been looking at these kinds of problems in 1960s. And so what do people use in practice to really solve this problem? Usually what's used is maximum likelihood estimator. So what does the MLE look like for this problem? So it can be, if we write down the MLE, what we note is, first of all, one thing I want to note is that it's not the empirical estimator. So for most non-parametric mixture models, when we write down the MLE, they're not often the empirical estimators that we would naively write down. Whereas in most of ML 101 or Stat 101, for a lot of examples, we see MLE and empirical estimates kind of coincide. But in this case, it's not. If we kind of massage this equation a little bit, what this turns into is that you're minimizing the KL divergence between the observed fingerprints and the expected fingerprints under distributions supported on 0, 1. So this actually is a convex optimization problem. So that's really nice. But the other thing I want to highlight is that this problem has a lot more challenges apart from what we've been discussing so far. One other thing I want to highlight is that this problem is actually not identifiable. So in the sense that if you only have T tosses per coin, you can think of this as like, bottlenecked by, like, even if I give you T moments for this underlying distribution, we will still have ambiguity as to what the true distribution is, because several distributions can match in the first T moments exactly and can be different, right? So in fact, there is a lower bound of 1 over T, and with respect to Wasserstein distance of like how well you could try to learn the underlying distribution. So let's keep that in mind in a few slides when I show the guarantees for MLE, kind of that kind of gets reflected. But before I tell about like the results that we obtained working on this problem, I want to give some idea about what was done in the past. So MLE in fact was proposed as a way to solve this problem by Lord in his first paper of 1965 of psychological testing when he was using this model. And several works actually have studied the properties of solutions to the MLE, like identifiability, the geometry of the problem, and so on. Like really a great set of works in 60s, 70s, 80s, and even like by Wood in late 1990s. And more recently, there was interest in kind of learning from small data. And there's a series of works that have been that have proposed like linear program based estimators, moment matching based estimators, which are really neat estimators. However, they can be shown to be optimal only in like a specific setting where the population size is exponentially large compared to the number of tosses. That is the if you look at the T being the number of tosses per coin and capital N being the number of coins, N has to be exponential in T. So that's when these newer estimates that were provided are optimal. So the question that we started asking is, okay, there's all these really interesting and nice nuanced new estimators. However, people have been using MLE since 60. So how well does MLE actually perform in this setting? And so we analyzed how well MLE does for this setting. And there is in fact two regimes. One regime is where the number of coins, that is population size, is exponentially large in the number of tosses per coin. And the other regime is where L is sub-exponential in T. And what we showed is that the maximum likelihood estimator is in fact minimax optimal in both of these regimes. So if you look at, so here I'm showing Wasserstein 1 distance on the y-axis, Wasserstein 1 distance between the true underlying distribution and the estimated distribution by MLE on the y-axis, and on the x-axis, I'm looking at the number of tosses per coin. So when T is less than log N, MLE gets a rate of 1 over T, and above that, it gets a rate of 1 over square root of T log N. There are matching minimax lower bounds. The lower bound for T less than log N was shown by a previous work, and we provide a matching minimax lower bound for T bigger than log N. So the nice thing about MLE is that when you're solving the MLE, you don't really need to worry about which regime you're in. You just give the data to the MLE and it spits out an answer. And when we analyze, what we see is that it actually gets the right rate in both of the regimes.
So that means it's optimal everywhere, or because you're separating into two parts, so optimal everywhere, or just like?
So it's optimal. So actually, there is continuity in the sense when T is like log N. So this is like 1 over log N. So there is, so that's like 1 over T as well. So there is continuity there. What we were able to push it only is like this kind of like fractional polynomial in N. But I think this can be, then this part I think is coming from the proof technique. I'll tell a little bit about that, but I do think it is optimal beyond as well.
What exactly
but I
is the
don't-
point?
yeah.
What happens there?
So there is nothing to, like, that's, so this part is just like, I think naturally the problems, this regime difference exists in the problem. That's coming from our proof technique.
Okay.
Yeah.
So what happens there? something stops or it drop like?
No, I don't think it stops. I'll tell you a little
Okay.
bit more. I'll get to that as to, so how do we, show the optimality for MLE in these regimes is, the key idea is to kind of look at the fingerprints, right? So what is MLE trying to?
Just go back.
Yeah. Yeah.
Right, so I'm just trying to see if as the number of coins increases. Then you.
So, yeah,
Yeah.
if the number of tosses per coin is fixed.
Right.
And if the number of coins increases, it really depends on whether the number of tosses per coin is in the regime of like being less than log n or kind of bigger than log n, right? Like, so it's like you fix n and like it's like if you fix t and you're only increasing n, then at some point you will be in this 1 over like, less than log n regime, because then if you're considering t as a constant. But if you are considering like t is kind of growing a little bit, then the question is like, is it growing like log n or faster, or is it growing like, is it just a constant or growing like less
So
than log
that
n?
was, so
Yeah.
is it clear that T has to grow with n, because like when we have more coins, you think maybe even for a fixed number, you'll be able to get.
Yeah,
get more
so
information.
so that's yeah, so essentially, so the bottleneck in this problem is that so maybe I can like go back a little bit about like, okay, so here's the setting, right? Like, so so you have some underlying unknown distribution P star of the biases. We are drawing the biases from that, and those both are unknown, and we're only having these binomial observations where T is the number of tosses per coin. So if we look at if I'm kind of so here I was like looking at the naive like empirical estimator, like if we estimated the coin biases like separately. So if you keep increasing n, what you can try to do is that you can get a better and better estimate of the fingerprint,
I see.
but not the underlying distribution. Yeah, and the other thing I want to highlight is that actually there is 1 over t is a bottleneck, because so even if we know the first t moments of the underlying distribution, you can have two distributions that are like Poisson 1 over t away, right? So there is that fundamental like problem
You
with,
want to get higher resolution as n increases to get.
yeah, so it's the so really if you wanted to increase your resolution beyond 1 over t, you would need yeah, it's yeah. And the key kind of technical detail in the proof is to when we are trying to bound the Wasserstein distance, Wasserstein 1 distance between the underlying distribution and the estimated distribution. So because we are having binomial observations, what we can try to look at is essentially what we get is this kind of binomial polynomial terms. And if you look at the expectation of this kind of polynomial, each term here would be the expected fingerprint. So one way, at least the technical kind of way we try to bound the Wasserstein distance is use the dual definition due to Kantorovich and Rubinstein. And so you have the supremum over all Lipschitz 1 functions, the difference between the expectation of the Lipschitz 1 functions under one distribution and the other distribution. So what we do is, instead of like, looking at sup over all Lipschitz 1 functions, we are looking at polynomial approximations for those Lipschitz 1 functions. And the natural basis for polynomials to look at in this setting would be Bernstein polynomials. However, it's not sufficient to kind of just look at what is the best possible approximation that we can get with Bernstein polynomials, because we also care about the coefficients that sits next to the Bernstein polynomial. So the key question to kind of really understand here is to provide those tight upper bounds in each of the regions. We need to understand how well can we approximate Lipschitz 1 functions using Bernstein polynomials while also bounding the coefficients. So let me illustrate that with an example. So here's the a simple absolute value function. It's Lipschitz 1. Here we're looking at functions supported on 0, 1. So if we look at, so in this example, I'm going to do just the polynomial approximation part. So I'm going to show examples with like degree 50. So if we use the classic Bernstein approximation scheme, which is for the coefficients, you take your domain and you uniformly sample the points in the domain. Like here, I'm looking for degree 50. I will look at 50 points uniformly on this domain and use the function values of those 50 points as the coefficients. So if we do that, the max coefficient is pretty small, which is good. It's a constant. And the error you get is something like 0.06. It does a good job of approximating everywhere else except like near 0.5 in this case. Now you can also actually get really, really good approximation with degree 50 polynomial for this function. However, if you and the way you would do that is we know that we can use Chebyshev polynomials to get really 1/degree kind of approximation. So we could use the Chebyshev polynomials of degree 50 and make it basis transform to Bernstein. But what happens to the maximum coefficients when we do that is they become extremely large. And this is why the previous works, especially when you're looking at moment matching kind of estimators, the bottleneck of like only being optimal in when t is less than log n is because in the t less than log n regime, the rate you can get is 1/t, and that kind of stems from because you have the 2 to the power t being kind of like if you look at how large the polynomials, the coefficients of the polynomials can get. If you're using degree t polynomial for your approximation, which is what we can do at max when we have t observations per coin, your coefficients can be as large as 2 to the power t. So what we were looking for here is okay, this is limiting in the sense that it only gives us optimality in a specific regime. But what about like this two extremes? So if this gives me, the first one gives me a rate of 1/square root of t, because it's a good coefficients, but bad approximation property. Great approximation property, but really large coefficients. So can we kind of have a trade-off in here? And in fact, you can. So you can give up a little bit on the how well you do the approximation, but you can get a control over the coefficients. And here in this example, what I did is actually lower the degree. So I used a degree 25 Chebyshev polynomial, and not only we increase the not only do I kind of like transform Chebyshev to Bernstein, but the nice thing about Bernstein polynomials is you can take this lower degree Bernstein polynomial and express that as a higher degree Bernstein polynomial, like in a fake sense. And when we do that, actually the coefficients in the larger, like a faked larger degree polynomial become smaller. And in the limit, in fact, you could, if you keep going, making degree for the Bernstein polynomial fakely larger and larger, you can actually get better and better coefficients, and the coefficients will essentially lie on the function everywhere. So essentially, what we prove, the key lemma that we show with respect to that is for any Lipschitz one function supported on 0,1, we can approximate that using Bernstein polynomials of degree t with the following uniform approximation error. So if you want to get the best approximation error possible, which is 1/t, then the coefficients can be 2 to the up to 2 to the power t. But if you're willing to give up a little, and if you're looking at 1/k approximation error, then you can bound the largest coefficients like e to the power k squared over t. So if k is like t, then we are back to being exponential. But if you're and if your k is like square root of t, then the exponential term goes away. So you get this kind of a smooth going from 1/square root of t to 1/t.
It having interpretation of like minimizing like a bias, that if you increase the degree, you kind of decrease the bias. Like maybe you increase the variance. Is there like an interpretation of that form that you're equated to or something?
That's a good question. So in this case, yeah, I need to think a little bit more about that.
So
Yeah.
in the sense that if you increase the degree, you can approximate and increase the bias, but
Yeah.
then you have higher variance because you're looking at high.
So in this actually, like in the scheme that I am using, I am actually not so the true degree is small, right? Like so the true degree I was using was 20, for the middle figure in the last, slide, it was just 25. And I was like increasing the degree by just making the Bernstein polynomial higher degree. But if you go and look at the actual degree of the Bernstein polynomial, it's actually still 25. But you can write it in terms of a polynomial that looks like a 50th degree one. So in essence, if you look at just from the polynomial point of view, I'm not really increasing the degree of the polynomial. So I need to like carefully think. That's a really good question. I need to think about this more. Yeah. Thank you.
So,
Yeah.
so when k equals to t, you don't recover that square root of t. You have t to the power 3/2 for.
So so when k equal to t, I get like exponential
Yeah,
in
the
t.
exponential, but the polynomial terms do not really.
So
match.
I think this term is, I don't think this term is truly
Should be
here.
there. Yeah.
Again, I'll in the next couple of slides, I'm actually very keen to hear if people have more ideas in there, because what I'm doing right now is, so I have explicit like formula that I can write down for the coefficients. So they are hypergeometric functions, but they're unfortunately none of the, like at least the ones that I could look at, I couldn't find the very well studied one that matches for these. And so currently the way I'm bounding this is just bounding it on unit circle and using Parseval's theorem. So I'm actually bounding each coefficient by the L2 norm of all the coefficients. So that's where the inefficiency of that extra t plus 1 and stuff is coming. So I think we can do much better, because this is the bound on like the L2 norm of all the coefficients. And I'm using that as a bound for each of the coefficients right now. And I think that's why we have like that, 2 to the power n to the power 2/9 and stuff is coming, because if we just like look at these and like put it in the analysis, that's what I end up like getting. But I do think we can, like I like when you plot these things, it's really like much better. I don't think this t plus 1 term should be there, sitting out. So if anyone has like thoughts on polynomial approximations, I'd be very keen to hear that. Yeah. Yeah, so I'll wrap up this part here, and there are many other like questions of like that are relevant for practice that come from these settings that the kind of naive way of writing down the model don't capture. One is that many times domain experts have ideas about like what properties should these underlying distributions have. So if we are taking that information into account, so what kind of rates can we get? Because right now, what we show is just minimax optimality, but if we are not looking at all possible underlying distributions from 0, 1, but restricting ourselves to settings where you have some certain properties, like can we do better?
People do make these assumptions in this, or is it or in theory?
So in practice, people kind of do, like you can encourage smoothness and stuff, but in theory, I haven't seen analysis which does like instance wise or even like a special classes. Yeah. And the other thing is that this is a model where everything we assume to be IID, but in many scenarios, for example, when epidemiologists are like looking at their data, we can think of like there's like a network for like that is underlying these individuals, and so there's these dependency structure. And also, of course, there can be features that is available to you as well. So how do you incorporate that side information? So there's a lot of very interesting questions to ask in terms of building how do we make these kind of techniques more practical and usable for real data settings. So we in Washington, I also had a chance to collaborate with biostatistics folks from Fred Hutchison, and they were really interested in settings where the data can be modeled as Poisson. So I'll very quickly go over. So this was the setting where this is applicable kind of from the single cell genomics. So I'm not an expert in single cell genomics, but from my understanding is that you have this technology that you can count like how much RNA is in like every, like if you have a set of cells that you're studying, and you can get a good count of how much RNA is in each cell, which I think is pretty amazing. So it's like for every individual, you can look at like, let's say n cell for that individual, and you can think of like each cell having, because these cells, even if they're like similar type of cells, the cells can have a lot of heterogeneity in them. So you can think of each cell having some Poisson parameter lambda. So you get these counts and you can try to learn the underlying kind of like, similarly, you can write like a mixture model. There is like an underlying mixing distribution of these Poisson parameters. You observe the counts and you can try to estimate the mixing distribution. And even in this setting, we also show that the ML is minimax optimal. And the nicer thing about the Poisson setting is it's actually identifiable. So at least the problem of identifiability doesn't exist here. And I suspect actually for probably one parameter exponential family, probably MLE is optimal. But that's just a conjecture at this point. What we did in this project was to actually build on these learned distribution, like what you can do with these learned distributions, like the motivation I gave you about testing. So that's what we were doing here. The high level we were looking at, okay, can we use these learned underlying distributions to design tests to see if there exists population level gene expression difference among different groups. So what we proposed is to use permutation tests that were using both the mixing and mixture distributions. So what you can do is you have K groups. Each group has a bunch of individuals. Each individual has a set of cells. So what we are doing is like looking at the data from each individual, fitting distribution for the cells for each individual, and then looking at how these distributions are different from each other when you're looking at individuals in a group versus individuals from different groups. So we applied it on single cell RNA sequencing data from autism spectrum. There is well-known techniques that people use in genomics called DES sequence 2. And when compared to that, what we saw is, so the red Venn diagram here is the DE sequence 2. The blue and the purple ones are the tests, the permutation test that is built on the mixing and mixture distributions. We were able to recover all the ones that was discovered by the previous algorithm, but in addition to those, the tests that we developed also come up with new genes. There are actually literature who also mention these genes with respect to autism spectrum, but I'm not sure whether there is scientific, like more literature where people have actually done experiments. But what this kind of opens up is potential to build tests that are more nuanced than for example, looking at if there is the difference in the mean of two distributions, for example. So kind of like learning these like non-parametric mixture models can really give us the ability to build potentially nuanced tests that can test for more differences than just looking at average differences between groups. Yeah, and then did you have a question? Okay. Beyond this, there are actually very interesting questions we can ask about when we are just learning underlying distributions in various settings. The other thing I wanted to kind of also mention here is another context where we asked this kind of, can we use the underlying, like learning something about the underlying distribution that gives us insight into a problem with less data than trying to kind of gather a lot of data ahead of time. So one of those settings is this multiple hypothesis testing. So usually, let's consider a scientific question where there is some 10,000 fruit fly genes, the Drosophila genes. Let's say some of them can inhibit virus growth, some of them can't, and the scientist is really interested in figuring out which of these 10,000 genes are helpful in inhibiting virus growth. One option is that they can go ahead and do like a large scale experiment, multiple replicates for each of the genes, and then try to figure out through multiple hypothesis testing which of these genes are significant. But even before going and doing a very costly full experiment, what the question we were asking is like, can we design a pre-screen method that will tell us, can at least give us like a estimate of the number of positive discoveries that you could make, and what would be the effect size of those positive discoveries. So you will not be able to make the discoveries yet because this is just a pre-screening level. But can we at least say, okay, if you go ahead and do this whole expensive experiment, you will at least make these many discoveries, and these discoveries will at least have this much effect size. Can we do that with number of samples that is much smaller than the samples that would take to really do the whole full-scale experiment? So here's an example of what I mean by that. So the distribution here is just a distribution over the kind of, you can think of that as effect sizes, right? So it's like if this was the distribution over the null hypothesis, usually what scientists do is like they'll like look at like an alpha of like 1% or 5% and say we're gonna like reject things that is above that. So what we want to do in our estimator is on the x-axis have effect sizes, and then the y-axis is the lower bound of the number of discoveries that we would make in each of those effect sizes. So what we can guarantee is that if you look at this effect size of 1, you will make at least 80. You can find at least 80 genes that would be above that. If you want something like 2.5, then maybe we can only guarantee at least 20. We don't know if you can make more than that, right? So then the question is, the scientists who have more domain knowledge can decide, oh, okay, only if the effect size is about 2.5 would it be meaningful for us, and maybe if we do this experiment, we can find only 20 genes or so, so maybe it's not worthwhile. Or maybe they realize that, oh, that's actually worthwhile, so let's go do that, right? Like, so this is just like a pre-screening method that can help scientists in kind of deciding which experimental design they would want to choose, depending on at what effect level they would want to do make their discoveries. And what we show here is that, in fact, the answer to this question is yes. If you are testing n hypotheses, with some mild assumptions of like we can only make comments about effect sizes that are relatively smaller, then we can detect the existence of discoveries, not making the discoveries, just detecting the existence of discoveries with much fewer samples than what you would need for identification. And this work was done with in collaboration with Kevin Jameson at University of Washington and his student Jennifer Brennan. So I'd like to like wrap up this part here. So I think there is like a lot of really interesting questions that we can ask that stem from non-parametric mixture models. And in particular, both kind of understanding how well we can like estimate the underlying distributions, but also for downstream tasks of what we can do with these like learned distributions. Okay, so what I want to do in the next few minutes is to kind of talk a little bit about metric and preference learning. So I'm switching gears a little bit here. I got really interested in this when I moved to Madison. I had a chance to talk to Rob Nowak, who's in Madison, as well as Tim Rogers. He's a professor in psychology in UW-Madison. And for several, in the last like 10 to 15 years, he's been using computational tools and techniques that come from metric and preference learning to really understand how we as humans make judgments based on our preferences. How do we even like our mental structures of different concepts? Like how do we think about some concepts being closer to each other and far away from each other and so on? In this setting, what we were looking at is like in preference learning, the question that you ask at high level is, you have all these objects and you want to understand how this person, like what this person's preference is for these objects. There's actually a very, very long and rich set of literature for preference learning. The one line of literature that mainly focuses on ranking, and another line of literature that's called ideal point model, which looks at both ranking as well as trying to learn the individual preferences themselves. I won't be focusing much on ranking literature here. I'll be focusing more on ideal point model, which kind of puts a geometry on this. You're like, ideal point model is as follows. Each of these items have some features, some representation in some known feature space. You model the user also in the same space, but we just don't know their preferences, right? So their preferences are also modeled in the same space. And the basic assumption in ideal point model is that when we ask this person, do you prefer like tomato or the pear? Their answer is going to be tomato if the distance between the representation for tomato is closer to their preference point than not. Okay, so that's the assumption of the ideal point model. And now given these kind of pairwise comparison, you can think about like lots of different tasks, including like ranking, for example, if you're in d-dimensional space, it roughly takes d log n pairwise comparisons to rank these items. And for those familiar with the ranking literature, if you are using like, if you're not putting this geometry and if you're just trying to do ranking using pairwise comparisons, if you have n items, it takes n log n pairwise comparisons to do the ranking. So if your number of items is much larger than the dimension, then it's helpful if you have a geometric structure. If there are features associated with your objects, then using that can actually kind of reduce the sample complexity.
These comparisons are deterministic or randomized?
So these can be either deterministic or randomized. So you can have randomized in the following sense. You can, what usually people model is that you can think of this instead of this answer being this way, you can put like a monotonic function of like with some probability, and probability can be, let's say, closer to like, the probability of error can be smaller if the difference of distances is very large. And if the difference of distances is like smaller, then there's more confusion. So you can put some models on it. So, but I don't think, I've not seen works that do kind of adversarial kind of noise. So mostly it is either flipping or like these kind of noise, which is more noise when you have more confusion and less noise when you have less confusion.
If you have noise, even if it's not adversarial, it's not super clear that you'll get even in the n log n, there may be any small, you care about smaller factors like
so these things are hiding some like other factors.
Okay.
So
Yeah,
I should probably put the tilde here.
Yeah, exactly.
There are lots of other factors that are being,
Okay.
good question. Yeah. So the basic idea when you're doing preference learning in the ideal point model is that if you didn't have noise, then if you make a pairwise comparison query, I can kind of say, even though the user preference is unknown, I can, if the answer to this question of do you prefer tomato or pear is tomato, then I can at least have, okay, this user is to the left of this hyperplane here, right? And then if I ask another question, I can like localize them much further and so on. That's kind of what a lot of the kind of underlying algorithms really like exploit this. Now, if you learn if you use the ideal preference point, you can actually try to localize the user preference. And the advantage of that, apart from ranking the given items, is that now if I have a new item, right? And I have already learned the user preference, then I don't need to make any more comparisons. I can figure out for any other object that is there in the space as to what this user would be preferring, how they would prefer it compared to other items. The other thing is we can also think of what's the best item for this user, right? So by definition, if there is an item at the user's preference point, that's the most liked item. And in some settings, maybe that can, you can have you could look at the profiles of like, flavors of the fruits. Here you are not generating a new fruit, but think of this as like generating a new fruit flavored drink or something, right? Like, so you can kind of generate new items if you want to. So the limiting thing that we found in the literature is that you are either in the setting where you take everybody's data and you learn kind of like an average model, and therefore you learn like a one preference point for everybody, or you ask those order D questions to like every individual and like really learn that individual person's preference point. And the other one is that to really use this kind of intuition, you need to assume that you know the metric. So to do this, I need to know how the people what is the distances people are using to make their judgments. So we wanted to kind of understand, okay, if we are moving forward from this and looking at diverse preferences that people have, and if we don't know user metrics, like what can we try to do? So that's what we looked at with my collaborators in the setting where you have multiple users and unknown metric. So there are K users, each user can have their own preference point. I also don't know the metric M. So the metric M is shared. So if you ask Kth user, do you prefer I or J? Their answer depends on how close I is to their preference point under a Mahabalonis metric M. So here, all these preference points UIs are unknown, and so is the common metric shared by people. M is unknown. So the goal is, can we learn the preference points of K different users and the common unknown metric from pairwise comparisons? And for those who are familiar with, I don't know if people are familiar with the triplet learning based metric learning literature. If you're familiar with that, I just want to make a comment that if I knew the user preferences, I can view these questions as a triplet query of asking, is Xi closer to UK or XJ user closer to UK? And so if I knew the user preferences, I could potentially use those techniques to learn the metric, right? And if I knew the metric, I could use the techniques in the preference learning to learn individual preference points. The problem here is we don't know both. And so can we do this simultaneously? And the answer is yes. So so Arya, how much time do I have?
Few minutes.
Okay.
Just,
So in the interest of time, I will not go into a lot of details of it, but what we do is we can cast this as with some variable chain, we can cast this as a nice problem that you can nicely write down like a convex optimization objective for this. And what we show is that if you have single user, you would need of the order D square. Again, I should put a tilde here. There's some factors that I'm ignoring. So D square comparisons. So if you have only one user and you're trying to learn both their unknown metric and their user preference, it's going to be expensive because the single user has to do all the job of learning both the metric, giving us the data to learn both the metric and their user preference. But if we have at least D users, then what we can do is amortize the cost of the learning metric among them. And so with only an order D comparison per user, we can learn both the shared unknown metric and separate individual preference points. So this is like, so if you recall, if I knew the metric, I need order D comparisons per user to learn their preference points. So with kind of similar cost per user, we can also learn the metric because you're kind of pulling in everybody's data to learn the shared metric part. And we did some experiments with color data set. I'm not going to go into the details of it. But what we noticed with this is that if you have lots and lots of number of comparisons per user, even actually potentially learning, like, what we were wondering whether, this assumption of a common shared metric makes sense or not. And so something that we are really interested in exploring is like, what if you have like settings where actually, like in the color data set, then we also see that if you have like, there's a very interesting data set collected by another psychologist in UW Madison, Karen Schloss, and she really is interested in understanding how people prefer colors. And they have these extensive data sets collected of like pairwise comparisons, like lots of pairwise comparisons per individual. And if we try to fit a separate metric for each individual, you can actually do the prediction even better. But of course, that's like a lot of cost per individual. So some of the directions that we're exploring right now is like, how do we kind of model this where maybe you can have like a subgroups that have slightly different metrics. But the problem is that, ahead of time, we don't know the subgroups because it's not easy to kind of just maybe use demographic information and something like that to just classify people ahead of time or cluster people ahead of time. So these are settings where like, okay, if there is a clustered structure, can we learn both the cluster structure and the separate models for each of those groups simultaneously? The other direction that I'm really excited about is also, what if we don't have enough data to learn the individual preferences, right? So you need, if there is like if I'm trying to learn a user preference in d-dimensional space, I have d degrees of freedom, so I need like a d observations to learn that. But there are many settings where I might not care about learning individual differences, individual preferences, but what if I want to just learn the distribution over individual preferences? So can we do that? And I'm gonna not go in a detail of what we are able to do, but we have just started to explore this question with my student, Gokjan Datli. And at least in like the setting, so the question is, can we learn distribution of preferences without learning individual preferences? And for very simple setting of 1D, the answer is yes. And at the higher dimension, it's a little bit more complicated. If you have, instead of preferences, if you get like a rating or a distances, then you can in higher dimension also kind of hope to learn the underlying distribution, but with just pairwise comparison, there is actually identifiability issue that comes up. And so we are like exploring like more questions with respect to like what kind of structure enable us to like learn the underlying distribution. So I'm gonna kind of wrap up due to time. But we are kind of excited. Maybe I'll show some of the this is with distances, like the true and learn distributions, like on the graph structures and like on kind of essentially there is hope to learn the preferences, but you might need to make some assumptions, like what are some of the assumptions that are meaningful for applications, and like how do we then have algorithms in those settings that work well is something we are exploring right now. And I'm gonna, so these are the references for the of the papers that I kind of presented today. And I'll be happy to kind of chat more offline. Thank you all for your patience, and if you have any more questions, I'm happy to take those. I didn't know if there were questions on Zoom.
There were none. There were at some point 30 some people on Zoom, but I think on the top of the hour, many people left. So
Yeah.
if is there any other questions that we have for yesterday?
Yeah.
I have a question. First of all, great talk. Thank you so much for giving it. So on the technical lemma, do you know if there's like, could that be extended to higher dimensional? Like, is that trade-off?
So you mean the preference one, right? Like the underlying distribution of preferences, or is it the first part of the talk?
The first part of the talk. So on
okay,
the
yeah.
thing about Bernstein and Chebyshev
Yeah.
polynomials.
You
now
can,
take
you
it
can
from
extend it to higher dimensions. So we did look at that. The difficulty there is, though, you will pay price for the dimension exponentially.
there. Okay, is that reflected in, like in both, like in the interpolation, or?
So you are trying to now approximate a function in d dimension, like Lipschitz one function in d dimension,
Mhm.
like using Bernstein polynomials in like again higher dimension. But because of the fact that you're trying to learn something well in high dimension, you are going to pay a cost.
I see, and that's not avoidable on either
Yeah.
end of it, right?
Yeah.
Thanks.
Yeah, good question. Thank you.
Maybe
Yeah.
about the multiple hypothesis testing.
Yeah.
So in general, like I think even the graph that you showed is not necessarily going to be the specific hypothesis, it's going to be continued. Like I think even your graph showed that right. Right, like the
Yeah.
graph, there's going to be continuum, and that continuum may be in higher dimensions, right?
Oh, that's a good, like here we are really looking at like the 1D, like we're looking at like so once scientists do these experiments, they collect all this data, they try like, and then they have like this z-scores that they come up with. And so we are looking at learning like the distribution of the z-scores and then trying to estimate for each effect size, providing a lower bound with guarantee of like how many discoveries would you be able to make at each of the effect size.
So you're
So-
going to force it into, even though it's a continuum, going to force it to like quantization levels. It's
So now we are not quantizing though. It's 1D, dimension is in 1D,
right.
but it is continuous. So what we are able to provide is a simultaneous guarantee for all effect sizes. That the curve that we have plotted is a lower bound. So if you're thinking about the CDF for this, like what we are like kind of like saying is that this is a lower bound of like what you would get in all those points, and it's simultaneous. We are essentially exploiting DKW inequality. And so our guarantee actually holds for all the effect sizes.
Okay, I think in the interest of time, let's just end here and thank you very much, Ramya.
Thank you.